Hello! So, in this video, this is kind of like almost the last piece of the puzzle before we move on to the non-homogeneous case. And we're going to basically be considering this thing called diagonalisation. Okay, so again, I've got my homogeneous system, linear system of ODEs up here. Okay, and hopefully you're sick of the sight of this now. I've got a three-dimensional case here, so dx by dt equals ax plus by plus cz. And likewise dy by dt and dz by dt. Like I say, hopefully you're sick of the sight of these now, because it means that you're kind of so familiar with them that you kind of get what they're all about. Okay, and we can basically write this system as like we have done in previous examples, as almost like a condensed version of this system. Just dx by dt equals ax. Okay, where x is just our vector of variables, so x, y, and z, and a is just our coefficient matrix. And it makes sense then that when we're looking at how to solve homogeneous cases, we use this matrix. Okay, because this matrix is what's going to set this matrix of coefficients. These coefficients are going to set this system apart from any other system. For example, if we have dx by dt equals 4x plus 3y, yeah, and then if we have another system which involves dx by dt equals I don't know, 7x plus 12y, yeah, well, fairly obviously you can see the difference between the two systems. Okay, this isn't a system, but just imagine we had dy by dt and dz by dt, or whatever, no, dy by dt as well. The thing which is going to set it apart is the coefficients, right? So anyway, that's kind of a little bypass. So this is what kind of the matrix of coefficients. What I'm trying to say is the matrix of the coefficients define the overall system. All right. Now, what I'm going to propose to you, by the way, this is called coupled equations, because you can kind of group them all together into one group, if you like. This is the system coupled into one place. But this basically means that we have to solve the system simultaneously. So in other words, we have to solve all equations at the same time, which is why we kind of group them together into this dx by dt equals ax fashion. Okay, but now I'm going to propose to you, what happens if we have an uncoupled system? So in other words, each equation only had one variable involved. So this is known as an uncoupled system. All right, because basically each variable only depends on one. Each equation only has one variable involved. So look, dx by dt only has an x. All the others are 0. So these kind of go away. And likewise, dy by dt only has a y involved. So in other words, the x and z go away. And likewise, dz by dt only has a dz involved. So in other words, the y and x terms go away. And this is what's known as an uncoupled system, because as you can see, dx by dt only depends on x. dy by dt only depends on y, and dz by dt only depends on z. And this is true for the nth dimensional case. I'm just showing it with a three-dimensional case. Okay, so therefore what I'm trying to say is, wouldn't it be good then if we can write this system up here, this system up here like this, okay? And this is an uncoupled fashion, okay? And so it's exactly the same kind of idea. It's just this time, instead of there being an A here, there's just a D. Okay, so the next question is, well, what is D? Well, D is a diagonal matrix. The reason why we call it D is because it's a diagonal matrix. As you can see, it's just basically all other elements. Hopefully you can see, maybe if I show you here, all other elements disappear, yeah? So they all go to 0, and you're just left with a diagonal along there, okay? And that's called a diagonal matrix. So I form a coefficient matrix, and it'll just be a diagonal matrix. So it's just the leading diagonal's got terms in. So basically what I want to try and do is I want to turn my system, my original system which I had up here, which again is defined by A, my matrix A, my coefficient matrix, into a diagonal system. So in other words, what I want to do is I want to turn A into D somehow, okay? Or at least I want to come up with an expression for D in terms of A, or in terms of things which are based on A. Okay, so the way which I need to do that is, first of all, I need to consider what information can I get out of A. Well, I can get information such as eigenvalues and eigenvectors. So I can get the eigenvalues, and of course there's a three-dimensional case. In other words, there's 3 variables, therefore means that there'll be 3 eigenvalues. Okay, and then I can also get corresponding eigenvectors out. So let's call them U for the eigenvector corresponding to lambda 1. Okay, V for the eigenvector vector corresponding to lambda 2, and W for the eigenvector corresponding to the eigenvalue lambda 3. Okay, so these are now what I want to this is what I can get out of my matrix A. Right, so I have my coefficient matrix A, and I can get eigenvalues and corresponding eigenvectors out of it. Okay. Notice that we're talking about fundamental solutions here. Or at least we're not talking about fundamental solutions, but we're talking about the eigenvectors are basically, these eigenvectors, U, V, and W, are linearly independent, which basically means that one cannot be written in terms of the other, in terms of the other one. Okay, there's no matrix multiplication. There's no multiplication which you can do to turn, say, U into V. All right, they're totally independent of each other, and that's true in general of all eigenvectors. So basically what I'm going to do is I'm going to form a matrix. I'm going to form a matrix of eigenvalues and eigenvectors. So two matrices, one of eigenvalues, and I'm going to call my eigenvalue matrix D, because it's going to be a diagonal matrix. Okay, and hopefully if you've got any kind of clue of linear algebra, which hopefully you should all do, that is kind of what when we work out eigenvalues, we only look at, essentially we form a matrix which consists of the leading diagonal. Okay, if you're not clear on that, go back to my eigenvectors and eigenvalue video, because that will really kind of hopefully make a bit of sense. Okay, and I'm going to do the same thing, forming a matrix of my eigenvectors. Okay, so U is a three-dimensional case. I'm going to say U is just the matrix U1, U2, U3. Okay. And likewise, I'm going to do the same for V, V1, V2, V3, and W, W1, W2, W3. So in other words, T, I'm going to actually rewrite it like this. So T is going to be U1, U2, U3. So I'm basically writing my eigenvectors as columns. So the elements in the eigenvectors as columns. Okay, so like that. So basically now I've got my two matrices. I've got T, which is the matrix of my eigenvalues. Sorry, my D, which is my matrix of my eigenvalues, and T, which is the matrix of my eigenvectors. Okay. Well, what do we know about eigenvalues and eigenvectors? Well, remember we work it out. Well, what do we know about the link between eigenvalues and eigenvectors? Because obviously if we can form a link between eigenvalues and eigenvectors, then we can form a link between D and T, these two matrices. Okay. Well, if you remember way back to first year maths, or at least if you've watched my video just recently, that we can form, that how we get eigenvalues and eigenvectors is like this, by solving the system of equations. So we solve the system of equations A, which is our matrix, times our eigenvector, and the theory is that there must exist some scalar value, which we call an eigenvalue, times by that same vector, which we call an eigenvector. Okay, and likewise we can do the same thing for V, okay, but this time with lambda 2, V, and the same thing for W, but this time with lambda 3. All right, so basically this is the whole kind of idea behind it. So this is a good link. Okay, from our matrix A we can get eigenvalues out, which then allows us to solve this equation to find out what our eigenvectors is. All right, so the same kind of theory is now going to be applied to find out what D is. So basically what I've got now is I've got A. Maybe if I make these things a little bit smaller, then get rid of that. Maybe if I make these things a little bit smaller. So I've got A. Actually, I'm going to pause the video. Okay, so this is now what the information we've got. We've got our matrix of coefficients A. We've got our what have we got? We've got our matrix of eigenvectors T, and we've got our matrix diagonal matrix, which is our matrix of eigenvalues D. Okay, and we've got this system here, this system of equations of how we find the eigenvalues and eigenvectors of each. All right. Now, what I want to do is basically just consider a very, very simple matrix multiplication. So I just want to consider what happens if we do A times T. Well, if we do A times T, are you happy that what we're going to end up with is the matrix A times our T, which is U1, U2, U3, V1, V2, V3. Maybe if I write these out a little bit neater. V1, V2, V3. and W1, W2, W3. Okay, well this effectively, are you happy that what I would just get is something that looks like this? Okay. Okay, which is of course just A times my matrix times my vector eigenvector U. Okay, A times my eigenvector V, and A times my eigenvector W. All right, so something like that. Right. Well, now I can use this system, or these kind of set of equations, to say, well, okay, AU is actually just lambda 1 U, and AV is just lambda 2 V, and AW is just lambda 3 W. All right. So that's the same thing. Well, if you have a look, that there is exactly the same as just doing. What's it the same as doing? It's the same as doing my eigenvector matrix, all right? Sorry, my eigenvalue matrix times my transformation matrix, my T matrix, sorry, which is UVW. So you're happy that this is just the same as D, which is my lambda 1, lambda 2, lambda 3 matrix, all right? That matrix there, times my matrix T, which is of course just UVW. Okay, I haven't written it in the right way, but never mind. Okay, it should be written down. But essentially, you know, that is what I've got. Okay, there, which of course is just equal to dt. Okay, so what did I start out with? I started out with at, and I've kind of shown that it's equal to dt. So I've shown that at, my matrix A times my T matrix, my eigenvector matrix, is equal to D, which is my eigenvalue matrix, times my eigenvector matrix. Okay, and of course, T inverse exists because I've said before the eigenvectors are linearly independent. T corresponds to the eigenvector matrix. Where's T? T corresponds to the eigenvector matrix, and the eigenvectors are all linearly independent. Okay, you can do this. You can do these calculations to verify. I've kind of cut out a lot of steps and just shown a very brief argument, but you can do a rigorous argument if you want. Go through and argue it for yourself. But because T inverse exists, then because it's eigenvectors linearly independent, which means that no eigenvector can be written as a combination of the other, can be written in terms of the other eigenvector. That essentially means T inverse exists, which means that then I can write an expression for D. Just take T over the other side. It's just by multiplying by T inverse, right? So this is T inverse A times T. All right. So this is now, I've come up with an expression. Okay, I know A, and I know T, which means that then I can find what the diagonal matrix is. Okay, so essentially what I'm doing is I'm transforming. It transforms. It shows, well, essentially what I'm doing is I'm showing that I can turn A into a diagonal matrix just by using a transformation matrix. Okay, and that transformation matrix is a similarity. Well, I'm using a similarity transformation. So if I multiply it by the inverse of T and multiply by A and T and multiply by T, I'll get my diagonal matrix out. So essentially I can turn my system, what did I start off with? Here we go, right up here. I can turn this system up here, right? I can turn this system into a system which looks something like this before I've done all my crossings out and stuff. So in other words, a diagonal system, all right? So just with a leading diagonal there. So in other words, I'll only have a leading diagonal, and I can put in, and all other terms disappear. We'll just go to 0, right? So I can turn my matrix my system into an uncoupled system. All right, just by doing this